couple more things here. And so let's see if this gets up and running. Okay, so I'm gonna maybe leave this be, and I'm gonna send a URL out in chat, and I think you should be able to go to this URL, and yeah, seems like it. And so I was trying to get Zoom to push higher bandwidth, and I just couldn't get it to do it, and I think that just might be part of the Zoom world. And so I'm gonna try to send that stream out because I have a lot of bandwidth. Yeah, I don't have a Twitch set up yet, but I did have a spare YouTube account, or yeah, a spare YouTube account. I meant that that I can stream to and make use of more of my bandwidth. And so if you check that out, that should be in the settings. You should be able to jack that up to a much higher definition. And so go ahead and take a look at that, or you can hang out in Zoom. The problem that I found with the tube, and oh, here it is. The problem that I found with the tube is that there's a little bit of latency, and I don't know how that would be inside of this chat and audio environment. It's not a super big deal, but I feel like Zoom has really low latency. Okay, so some announcements on the day. Exam 1's going to be Tuesday of next week. That will take place at 7:30 p.m. An FAQ about just common errors associated with data entry and stuff like that comes out today. And then where would I think I would want you to be in terms of your studying? I would, oh yeah, that hourglass is a little freaky. Okay, let's hope that doesn't happen a lot. If things get wonky, I'm going to shut down the stream and just go Zoom. But where I think I would like you to be at in terms of problem solving is to do some problems. And as you do these problems, you're going to want to start thinking about what are the things that you need to get problems off the ground, and then what are the things you need to keep track of during the problem. Where are your trouble spots? Those are the types of things I think you want to put in your study guide. Okay. Next, what are we going to talk about here? We're going to talk about autonomous homogeneous linear equations. Those are all modifiers to the equation. So the equation is autonomous, it is homogeneous, and it is linear. So we're going to start off with reviewing the language of superposition, and then I'm going to bring in the language of Wronskians and linear independence that we had left kind of hanging last time, but we'll bring that in today. And then I'm going to talk about where things are headed in terms of the types of problems and how we're going to do the problems that are coming up. None of this second order stuff is on the exam. That was a question that was asked to me in email, but yeah, no second order material is on the exam. Okay, it's only first order stuff. So I'm gonna bring over my screen 2 now, and this is, I'm gonna leave mildly faded because I also increased my picture-in-picture size, and so I'll just leave this mildly faded so you can see through me, and then in the next set of slides I will have it full on. But the idea is we're gonna treat higher order equations. What are higher order equations? You take the derivatives of the function y and y itself, you make sure they're raised to the first power, and then you add them together, right? That is the main structure. Anything else that's going on with respect to the independent variable does not matter, okay? The independent variable t, or if that's x, that does not change the linearity of the equation. We're going to focus our attention on second order equations. Second order equations are going to be y double prime times some t mumbo jumbo plus y prime times some t mumbo jumbo plus y times some t mumbo jumbo, and then some right hand side. That's going to be the game. Right? That's our equation, our fundamental equation. I can supply that equation with either initial conditions or boundary conditions, which was where we were at last time. And then what we want to know is, given equation 2, the solution structure is as it was for first order, homogeneous plus particular. It's just that the homogeneous solution for this second order problem will be made of a superposition of 2 solutions to that same problem. So that's the game, that's the language. I think that the best way to go forward now is to visit problems and visit them while bringing out the language, right? We can sit here and talk about the language all we want, but down deep what we want to do is we want to take a look at some problems. Okay, so I'm going to fade out and move us to a quick review of this slide, right? We had this slide which said y double prime minus y is equal to 0. Well, that's the same thing as telling me y double prime is equal to y, which then asks the question, find me functions such that when I now take two derivatives of those functions, I get the same thing. And those functions are going to be e to the x, because I differentiate e to the x to get e to the x, differentiate one more time, and what do you know? I'm back to e to the x, where I started. But then e to the minus x also works, right? Because if I take a derivative, a negative comes out front, and then I take another derivative, those negatives cancel with another one coming out front. And so that will get me back to the same spot too. And so that is the types of things we're on the lookout for now. In these sorts of problems. And so we had initial conditions and boundary conditions. I think it just makes sense to do another. Okay, so what we're going to do is we're going to scroll on up to this problem right here. I'll go full and then I'll stay out of my picture-in-picture here. And so now I've got this problem. Y double prime plus y is equal to 0. And then we have some initial conditions and boundary conditions. Let's see how that affects. But the first thing we've got to do is we've got to solve this equation. Okay? And when I solve this equation, what am I going to do? I'm going to bring the equation down and I'll rewrite it. This isn't how we're going to do things generally. It's just these two equations lend themselves to mathematical puzzling. And so for this mathematical puzzling now, we're asking the question, hey, find some functions where if I take two derivatives of the function, I get the function back, but not quite. I get the negative of that function back. Good question, Sage. When I get to the boundary condition part, well, it's boundary condition. It means boundary condition. And so when I get to that part, I'll lay into that language pretty heavily. But getting back to the question, what functions are out there such that when I take two derivatives of those functions, I get negative of what I've started with? Yeah, those functions are going to be sines and cosines. So y1 of t is going to be cosine of t, and y2 of t is going to be the sine of t. Okay? So these are the functions that satisfy the word problem, right? And then now that I have two functions to the differential equation, I need to think about what am I going to do with these two functions? Well, now the implication is that I'm going to write this as y of t is equal to c1 cosine of t plus c2 sine of t. And so what is going on right here, this thing is the superposition or what is also called the linear combination of the two functions. Okay, so if you find two functions that solve the same homogeneous second order problem, then I will linearly combine them, or what's called in physics oftentimes superimpose them, or form a superposition, where I just take those sines and cosines, multiply them by constants, and then add the two together. Okay, and so just a real quick note here, if I take the second time derivative of this superposition, which is c1 cos t plus c2 sine t, well, what is the derivative going to think about the addition? Well, derivatives love addition, right? Because it just breaks them off into multiple pieces. So what this second derivative is going to do is act on c1 cosine first and add that to it acting on c2 sine next. But if c1 and c2 are constants, they don't care if they're inside the derivative or outside the derivative, right? So this is just going to be c1 times the second derivative with respect to t of cosine plus c2 times the second derivative with respect to t of sine. But what is the second derivative of cosine? Well, it would be take the derivative to get negative sine, take another derivative, and I will get negative c1 cos of t. And then what's the derivative of the second derivative of sine? I take one derivative to get cosine, take another derivative, a negative pops up, and what do I have? I have negative c2 sine t. But then I can factor that negative off, and I'll have c1 cos t plus c2 sine t. But what is c1 cos t plus c2 sine t? Well, that is just what I had written down before, and that's exactly why. And so, what is this equal to? This is equal to negative y. And so what have we shown? We've shown that the second derivative of y is equal to the negative of y, only we've shown it on the superposition. And so the moral that comes out of this that we want to take forward generally, and one could show it generally, is that the superposition of solutions to a linear equation is again a solution to that equation. That's probably the bigger, fancier talk for just saying, what am I supposed to do? I've got a second order equation, it's linear, I go on the hunt for two solutions, I form their combination, and then I have the solution to the system. I'm actually getting a little ahead of myself because what we're assuming here is that it is the general solution to the equation, and I'd like to talk a little bit about that right now before we do some initial conditions and boundary conditions. Okay, but first, are there questions? Okay, second, through your reactions in Zoom, could you just give me some idea of how many people are following the stream and not the Zoom? Is it boundary? Is boundary just min and max? No, I'll talk about boundary when I get there. Let's hold off. Yeah, it's a good question about whether or not there are 27 watching the stream. Okay, thanks. That's great. That's great. Yeah, that's totally what I need. Okay, and then is the definition on the stream good? It's better. Okay, stream is, okay. Okay, cool. All right, it's just going to be a little delayed. Last I saw, I think it was about 4-second latency between what goes on here and then the stream. Audio is even better. Oh, man, that's great. Cool. Well, hopefully I can keep this up. I'll probably try to move to the Twitch platform because, yeah, every time I played music in the background, YouTube started immediately showing me nasty messages. Okay. So, the application of the initial condition. Okay. The initial condition step is going to look like the following. What is it I know? IC means initial condition. I know that y it times 0 is equal to 1. So that means y it times 0 is equal to 1, which is equal to c1 cos 0 plus c2 sine 0. But sine of 0 is just 0. Cosine of 0 is just 1. So what comes out of this back end here is just a c1. So what have I found out? Yeah, c1 is equal to 1. Okay. Now what do I need? I need y prime of 0 is 0. So what is y prime? Y prime is of t is going to be take the derivative of cosine to get minus c1 sine of t. And then take the derivative of sine to get plus c2 cos of t. Now put in the initial condition to get y of 0, or y prime of 0 is equal to 0. That tells me that negative c1 sine of 0 plus c2 cos of 0 is equal to 0. But what is sine of 0? Sine of 0 is just 0. What is cos of 0? So cos of 0 is 1. So what have I found out here? I found out that C2 is equal to 0. Okay. And so if this linear combination is the two-parameter family of solutions, then after application of my initial condition, I have y of t is just equal to cosine of t. Okay. So what that's saying is that of the family of sinusoids that are listed right here in superposition, the one set of sinusoids that goes through 1 when time is 0, and 0, or in its derivative, goes through 0 when time is 0, is the cosine function, right? What is cosine when t is 0? It'd be 1. And then take the derivative of cosine, what do you get? You get the sine function, but what is the sine function when t is 0? It's 0. Okay? So now, the initial part. That was a question that was asked. Okay? The initial part of the initial condition. The initial part of the initial condition comes from right here. What you are saying is the following. I'll just get to the physics of the matter. This equation right here is the equation for a mass tied to an ideal spring that is not being poked at externally and is subjected to no drag. Okay? So, what this is saying is relationship between acceleration and displacement for that mass spring system, and the initial conditions are saying, hey, what's your initial displacement mass spring system? And what's your initial velocity mass spring system? You can think about the initial conditions is, if this is going to be the system with the forces, then the initial conditions are going to be how that experiment is initially set up in terms of its initial displacement and initial velocity. Okay? That is different than boundary conditions. Boundary conditions for the B, or the boundary conditions B part, what the boundary condition is saying is, I'm not going to tell you about the function and its derivative at the same point in time. What I'm going to do is tell you about the function twice at two different points of space. So the boundary conditions have everything to do about the fact that you're not stating the same point in time, you're stating the same point in space. So to drive that home in this boundary condition part, what I'll do is I'll say y of x is equal to c1 cos x plus c2 sine x. And then if I tell you that y of 0 is equal to 0, that says c1 cos 0 plus c2 sine 0. Well, sine of 0 is 0. Cos of 0 is 1. So what have I found out? I found out that c1 is 0. Yeah, good question. So it's being asked in chat, was there an initial question or are we just exploring the math? Well, I guess the initial question would be solve this ODE, and then question 1 is apply the initial conditions to find the one solution right here, which I guess I'll box in purple. That is the outcome of the first question. And then the second question, same ODE, is, hey, what's the solution if you imposed these conditions instead? And so if I found out that C1 is 0, I have this other boundary condition to apply. So now I have y of pi. Well, I've already found out that C1 is 0, so I don't need this term. And now I have C2 times the sine of pi. But isn't that, what's the sine of pi? Yeah, so I'm going to have a C2 times a 0, right? And then that's equal to 0. So what that tells me is that C2 could really be anything. So I found out that C1 is 0, C2 is any real number, and the solution to the boundary value problem, which is very different, I'm going to write in terms of the spatial variable x, is just going to be C2 times the sine of x. And what you'll notice here is that the amplitude could be whatever it wants, because what we've really just found here is a whole family of sinusoids whose amplitudes don't matter but are 0 on both sides. Okay? So why would a problem like this come up? Or how could a problem like this come up? A problem like this could come up because what you're really looking for are shapes. Shapes of maybe a string that's allowed to bow, but the string must maintain 0 displacement on the left and on the right. So boundary conditions have more to do with things like guitar strings or stringed instruments, and initial conditions have more to do with force laws and experimental setup. Okay. All right. So I'm going to fade out there. I'm going to freeze the screen for a minute. In my changes, so they are both two different solutions to the problem. There are actually two different problems going on. The brown problem, having to do with the boundary conditions, and then the purple problem, having to do with the initial conditions. Yeah. Yep, cool. And so something I lost in my re-rigging was the ability to effectively take screen caps. I mean, OBS will do this, and I'll set up OBS to do this. I just didn't set that up. I was working on other things. So I'll freeze here. You can take down any last notes that you want, and then I'm going to move us to another set of slides, which are in the shared drive in the general landing zone, and they are lecture notes number 18. Should we always use the x variable for the boundary conditions? I'm kind of habited to do so because when I'm doing this sort of math in particular, I'm thinking very much about how it relates to the contextual problem that I'm doing, because that helps guide me. So boundary conditions, I think boundary, I think space, I use the variable x. Initial conditions, I think initial, I think time, I use the variable t. Is there a relationship between the two solutions? Nathan, no, there's not. There really should be thought about as different types of problems, all coming from that one differential equation. All right. So, oh, sorry. I went over to the slide. Okay. What I'd like to talk about now is what it is we're going to be doing for basically the majority of the course. I'm gonna put myself up here. I'm gonna hide those little notes, and that's fine. For the majority of the course, we're going to be attacking a very specific problem, a very specific second order problem. We're going to use a variety of methods on that second order problem and get uber familiar with that problem. It is ubiquitous in STEM. It comes up when you're studying electromagnetic phenomenon. It comes up when you're studying quantum mechanics. It comes up when you're studying Newtonian mechanics. It comes up when you're studying wave motion. It comes up when you're studying like gravitational and magnetic potentials. It just comes up. And so if there's something we walk away with from the course, it is how to do battle with this equation, and to be able to do that without thinking, with just getting the paper to the pen and doing work on it. Okay? So there are some things that I'd like to highlight in terms of language before we get going. The first thing is this idea of a linear combination. Okay? Linear combination, we need to understand, is the same thing as superposition. So what does it mean to linearly combine things? It means to take the things in question, here it's y prime, and y double prime, multiply them by constants, and add them together. Okay? You do this all the time. It's just that we've never really named it. Like when you write down the solution, C1 y1 plus C2 y2, or like C1 cos plus C2 sine, which is what we did, we formed a linear combination. But when you did homogeneous plus particular, that was a linear combination as well. So if I were to give some language here, I would say that this first equation here is the linear combination of derivatives. Okay. This second equation here is the linear combination of solutions. Okay? So that is language that's common in mathematics, and the sooner we get down with that language, the better off we'll be. It's used all the time in mathematics. Take the thing, multiply by constant, add it to another thing, multiplied by constant. So what else would I say? Well, a question comes up in mathematics, which is, what if somebody plays the tricky game of saying y and then another y and then another y? So they give you this grab bag of the same stuff. A question that you can ask in mathematics is, if you give me a grab bag of mathematical objects and I'm going to make linear combinations out of them, then how do I know I have the essential set out of that grab bag? So maybe what I'll do right here is I'll sneak a little bit more up into this title line. And so let me tell you about another place you were making linear combinations. If you were going to say x vector is in R2, right? That means that x is some point in the plane at the tip of a vector, right? And how would you write that down? Well, you might have experience where you say that's C1 times I hat plus C2 times j hat. This is the superposition of I hat and j hat. This is the linear combination of I hat and j hat. Right here? Yeah, derivatives. And so, what is a linear combination trying to do? It's trying to say, hey, I hat's an important thing. I'm going to multiply it by constant so you have control over how much I hat to use. And then j hat, that's an important thing. That's another element, and you have C2's control, so you can control how much j hat to use. Well, what's the point of doing this? Well, that means using I hat and j hat, I can write down any vector I want in the R2 plane. Or think about it this way. Think about in your geographic mind, where does I hat point? It points this way, right? It points to the east. Where does j hat point? It points north. And so what this statement is saying is, I'm going to give you east and I'm going to give you north. You can go any amount in the east direction, or it's negative to get to west. And any amount in the north direction, and it's negative to get south. And using those two directions, can you get anywhere you want on a map? Sure thing, right? Now, what we want to do is we want to figure out, do I have exactly the right stuff, right? Because if somebody was giving me directions in north and south, north and east, that makes a lot of sense. But you could have in the grab bag north, east, and then northeast, right? You could have those three vectors in the grab bag. So mathematically, what we want to do is to define something that says, yo, your grab bag has way too much stuff. Just dwindle it down to this important subset, right? Like, why are you giving people directions using northeast? Just use north and east and west and south, and then they would thank you. Okay, so that next term is a term called linear independence. Linear independence is the following idea. Mathematical objects are said to be linearly independent if and only if the way to solve their combination equation is to set to zero, or their combination equation set to zero is by making all the coefficients in the combination zero. Okay? let's take a look. Let's use our east. Oh, I don't want west. I want east here, right? I hat points in the east direction. So, what I have here is C1 times east plus C2 times north. That is meant to represent this equation up here, except where are you going? At the end of the day, when you get done, west? Yeah. When you get done with your movements, your travels, where are you at? You're at the origin. So then the question comes up, how far should you go east or west? East. And how far should you go north in order to arrive at the origin of the plane? You should go none much east and none much north, right? And so if you have as your vectors, your mathematical objects, east and north, well, then somebody would say, if you want to go to the origin, you should go none much in either of those directions. And by these two constants being 0, and that being the only solution to the combination equation, that says that the vectors, the objects, the mathematical objects, are linearly independent. Okay. What does that look like for us? That looks like C1y1 plus C2y2. Now instead of I hat and j hat, my important things are y1 and y2. If I set them, that C1y1 plus C2y2 equal to 0, and the only solution to that equation is C1 is equal to C2 is equal to 0, then I would say that the functions are linearly independent. Okay? All right. Just saying all that out loud and just having a vibe for how class normally goes, I feel as though we should move on to an example and then try to double back around for this red note here. I feel like people need to put pen to paper. Question in chat, shouldn't it be C1x plus C2y? No. And let's do an example to highlight exactly that. So I'm going to fade out. I'll be coming back to this screen again. I'm going to freeze. But let's just see what this looks like in terms of our ODEs. This is a point in the course where it starts getting a little meta in terms of the mathematics. This is stuff that's really covered in gross detail in a linear algebra course, which I would encourage everyone to take. I think it's that important in the modern era. But we're in a DiffyQ course. We want to see this related to things that have tick marks on them. So let's do that. Okay. Okay, switching over to a new slide in 3, 2, and 1. All right. Here's the game. Don't worry about all these other notes that I have written down. It's all meant to terrify you, but really we want to start up here. We've got this equation. We want to solve it. If this middle term, this y prime term was gone, I'd probably be able to make headway here, right? Because it looks pretty much like a problem that I've done. But I have that term. There is a y prime term. So this is going to be the trick. I'm going to run through this trick once, and then I'm going to have you run through the trick as well. The trick revolves around the following idea. Exponentials were coming up all the time for first order problems, for linear ones, and so my hope is that the exponential can come back again and help us out. So what I'm going to do is for this equation, I'm going to assume that my solution looks like e to the mx, where m is an unknown constant, and my goal is to find m. Okay. So, again, the beauty with DiffyQ is I can always just guess and then see if I'm right. And I'm going to be right here, so that's good. But if that's my structure for my function, what's the derivative of e to the mx, where m is an unknown constant? It's going to be m e to the mx. Well, this is a second order diffie-q, so I need to take a second derivative here. And if I take a second derivative, what's the derivative of me to the mex? Right? I take another derivative. M is an unknown constant, so that m comes down, and I get m squared e to the mx. So what am I going to do with all this razzmatazz? I'm going to take this razzmatazz and I'm going to plug it into the original ordinary differential equation. So that means that y double prime plus 5y prime plus 6y is equal to m squared e to the mx plus 5m e to the mx plus 6 e to the mx. But then, what does each of these terms in my equation, where I've shoved in my guess and its derivatives, what do each of the terms share? E to the mx. So I'm going to factor that out. I get e to the mx. I see the question in chat. I'll address in just a second. Then I'm left behind with m squared plus 5m plus 6. And what should all of this equal? This should all equal 0. Okay. Is e to the mx ever going to be 0? No, it's not, right? So that means this parenthesed quantity has to be 0. And what that means is that I need to solve the equation m squared plus 5m plus 6 is equal to 0. And now here you are in the 4th course in a sequence of calculus courses at a STEM college, and what has appeared before you is, what sort of equation is this? Yeah, it's a quadratic equation, and what am I asked to do? I'm asked to find the roots of that quadratic equation, and so what do you know? What does this factor into? This factors into m plus 2 times m plus 3. And so what are my m values that would satisfy this? M is equal to -2, and m is equal to -3. So how many roots are to this quadratic equation? There are 2. So how many y of x functions can I find that solves this differential equation? There are 2. And so what I find out, and I'm about to hit that older chat question now, is that y1 is equal to e to the -2x, and y2 is equal to e to the -3x. Okay. So there was a question up in chat earlier with, would y of x normally be given, or are we going to have to derive it? Sean, for the time being, y of x is always going to be e to some number times x, or t, if I use the t variable. This is the function that's going to get us through 90%, 95% of the rest of the course. It is just that important. Okay? So now I have 2 functions that solve the differential equation, and so we want to notice, if I set c1 e to the -2x plus c2 e to the -3x equal to 0, then if I want to try to solve that equation, I get c1 e to the -2x is equal to -c2 e to the -3x. And then the question comes up, can you find a function c1 so that this e to the -2x will ever be equal to this e to the -3x over here? Yeah, good idea, Sean. Sean is saying e to the x in the chat, which is fine, except that's a function. I'm asking for a number. Is there a number I could choose right here so that this e to the negative 2x is equal to this e to the negative 3x, where I'm just kind of pretending this term here is 1? And the answer there is 0. Yeah, that is the only number that I can put in front of these exponentials, because these exponentials are totally different because the rates are different. There's no amplitude I could give one exponential so that it looks like the other. Okay? So what this implies is C1 is equal to C2, which is equal to 0, which implies that these functions are linearly independent. Okay? And since they are linearly independent, y of x is equal to C1 e to the negative 2x plus C2 e to the negative 3x, and this is my answer. So that's the game. What are the key marks? Let me go through with highlighting here. The first key mark is to assume an exponential. My next is to arrive at the corresponding quadratic equation, and from that quadratic equation, find the roots. Once the roots are known, we're going to talk a little bit more about the linear independence in the days to come, but really what you want to do is, once you know those roots, if you trust what you've done, you put those roots back in the exponents, and then once you put those roots back in the exponents, you linearly combine your results, and that is the solution to the problem. We are in our 4th semester of calculus-based learning, and for the next few lectures, we're just going to be solving quadratic equations. That's going to be our goal. Okay. Questions? Okay. So what I'll do is I'll fade out, I'll freeze. Are we going to solve for the constants? Not right now, Sean, since we've already done some initial value problems. I'm going to let that sit, and I'm going to ask you to take the first part of this technique through with a different problem in the time that we have together today. So I'm going to switch over to the next slide. There's some things here that I haven't talked about. I will talk about those things, but I think we need to strike while the iron is hot, and I think we need to strike this. It is coming on screen in 3, 2, and 1. All right, I'm going to come back. I'm going to put the 2-minute timer up, and in that 2 minutes, I want you to replicate those steps. And in case you didn't write it down, I'm going to say assume y of x is equal to e to the mx. All right, coming back. So let me scratch out. So I have all the steps in the last problem. What I want to do is I want to shrink those steps, because in the long run, what are we going to do? We're going to get pretty fast with this process because it just ends up with root finding. So what I'm going to do is I'm going to now write the steps that I would have if I wanted to shrink a little bit. I'd say y double prime plus y minus 2y. If the problem was maybe written in a book, I'd write this. And now I'm going to say, hey, what's two derivatives of e to the mx? Well, that's going to be m squared e to the mx. And then I'm going to add to that one derivative, so I'm going to have plus m e to the mx, and then minus 2 times e to the mx, where there are no m's out front. And now I factor that e to the mx off, and I get m squared plus m minus 2, and this is all equal to 0, because that's what my diffie-q is equal to, right? The derivatives are on the left, 0 is on the right, so here's my derivatives in my new e to the mx language. There's 0 on the right, so I get the equation that m squared plus m minus 2 is equal to 0, but what is that? Isn't that like m plus 2 times m minus 1 is set equal to 0. So it turns out my m's are equal to negative 2 and m is equal to 1. I have two different roots, therefore I have two different exponentials. If the exponentials have different exponents, then they are linearly independent. And what do? I write out my solution, y of x is equal to c1 e to the negative 2x plus c2 e to the x. Okay. What I want to point out is the following. If I write I'm going to go through in pink. If I write a 1 right here and a 1 right there up in the diffie-q, I haven't changed the equation. But what I want to point out is that there's a 1 right here and a 1 right here in the polynomial. And so the next thing I want to cut out is I want to just cut out this entire middle piece, because there's a direct mapping between the coefficients in the linear ODE and the coefficients in this quadratic equation. So if you give me the ODE, I'm going to be able to write down the equation, the quadratic equation, lickety-split. So let's take a look at one more before we're done today. And so question, I want to do this in one step. The step is to assume y is equal to e to the mx. Tell me, what is the quadratic equation that would come from this? For anybody out there that's seeing it. Ultimately, this is where we want to get in terms of expediting this process. It'd be m squared plus 6m plus 9 is equal to 0. Right. But then m squared plus 6m plus 9 factors into m plus 3. Quantity squared is equal to 0. And then m is equal to negative 3. So what I have is one solution, which is e to the negative 3x. Then the question is, what is the second solution? Well, the second solution I will tell you, and then after the exam we'll come back and we'll finish up this discussion. The second solution needs to be different than the first solution, and e to the negative 3x isn't going to cut it, and so the second solution is x times that. Okay? Now, I'll explain why that is next Friday. So if you're looking at the worksheet, you can know this right, and use it. But we'll talk about that on Friday. And then what's another type of root that can come out of a quadratic equation? We have real roots that are different. We just saw real roots that are repeated. And then the last is going to be, yeah, imaginary numbers are going to get involved. And then you've got to start asking the question, what does it mean for an exponential to have an imaginary in it? But we're going to hold off on that. And we'll call it for today and have a good weekend. Matt, in chat, you're asking, what about the C1 on Y1? When you add everything together, that's when you'll bring the constants in.
Recording stopped.